Despite the anomalies and contradictions that were covered over with obtuse mathematical equations, the world was only too eager to use Einstein's theories to construct a new understanding of the cosmos. To date, every theory advanced in modern cosmology abides in unswerving obedience to the limitations that Einstein's relativity laws require. But since the special and the general theories of relativity contradict each other, and both contradict quantum mechanics, this confusion led to an assortment of dubious cosmological theories that could not stand under the weight of their own postulates. To begin, as Newton did before him, Einstein envisioned a static and infinite universe. Newton was drawn to an infinite universe because it was the only way he knew to explain how the gravitational attraction of all the bodies in the universe could be counterbalanced so that the universe would not collapse in on itself. Einstein believed the same, and he developed an equation to show the stability of this universe, his famous tensor field equation. This equation simply says that the inward force of gravity, g mu nu, is counterbalanced by the outward force of energy, 8 pi tau mu nu, and thus the universe can remain steady and stable. Maintaining a stable universe was paramount. If there was any unsteadiness, it necessarily meant that the universe would have collapsed or dispersed at some point in the infinite past, and thus it could not exist at the present time.
The stability was knocked on its heels, however, when in 1929, astronomer Edwin Hubble discovered something peculiar about the galaxies. He noticed that the light of each galaxy exhibited a shift toward the red end of the spectrum, except a few galaxies in our local area.
According to Hubble's analysis, the red shift could be due to one of two things. Either the light lost energy as it traveled through space, or the wavelength of the light was being stretched. Although he admitted he could not be certain, Hubble sided with the view that redshift was due to a stretching of the wavelength, which he then further speculated was caused by the galaxies expanding away from the Earth. He reasoned that the higher the redshift, the farther the galaxy was from Earth, and the faster it was receding from Earth. Hubble showed this relationship by a chart in his 1937 book, The Observational Approach to Cosmology. Hubble's new theory of an expanding universe became an acute problem, however, because it meant the universe was not steady. In other words, in the distant past, it would have eventually collapsed or ripped apart, and thus could not exist today. A solution to this problem had to be found, which usually means that the scientists are going to readjust their mathematical equations to produce the desired universe, even though they have little empirical evidence that will support their desired universe. Accordingly, Einstein tweaked his field equation in order to counteract Hubble's expanding universe. He thus changed the equation to g minus lambda equals 8 pi tau. Lambda was given no precise value, much less an identity as to what kind of force or matter it could be to retard the presumed expansion of the universe. It became the mysterious figure that satisfied whatever was required to slow down or stop the expansion of the universe and keep it steady. Common sense, of course, reveals that this solution was doomed to failure, since if an expanding universe is eventually pulled back, then it would have collapsed in the infinite past and therefore could not exist today. In any case, adding an arbitrary component to make Einstein's equation balance against the data demonstrates how easy it was, and still is, to create mathematical equations that give an aura of knowledge and understanding. In reality, lambda was just an ad hoc adjustment to make Einstein's general relativity theory conform to Hubble's interpretation of redshift. As the famous 20th century historian Arthur C. Clarke once said,
"The lesson to be learned from these examples is one that can never be repeated too often, and is one that is seldom understood by laymen who have an almost superstitious awe of mathematics. But mathematics is only a tool, though an immensely powerful one. No equations, however impressive and complex, can arrive at the truth if the initial assumptions are incorrect. It is really quite amazing by what margins competent but conservative scientists and engineers can miss the mark when they start with the preconceived idea that what they're investigating is impossible. When this happens, the most well-informed men become blinded by their prejudices and are unable to see what lies directly ahead of them. What is even more incredible, they refuse to learn from experience. They will continue to make the same mistake over and over again. Some of my best friends are astronomers, and I'm sorry to keep throwing stones at them, but they do seem to have an appalling record as prophets.
Irrespective of Einstein's ad hoc adjustments, Hubble had quite a problem himself. If the cause of redshifts was not because galaxies were at differing distances from Earth, but because the galaxies all had an increasing velocity away from Earth, this meant the universe had a beginning, since logic requires that if there is a present expansion, there must have been a point in which the expansion started in the remote past. But Hubble's original calculations would only allow 1.5 billion years for the origin and expansion of the universe, about 10 times shorter than what was desired for the theory of biological evolution. As Hubble puts it on page 43 of his book,
"The age of the universe is considerably shorter than that permitted by the linear law. The maximum permissible span appears to be of the order of 1,500 million years. The initial instant clearly falls within the life history of the Earth, probably within the history of life on the Earth. Thus, the familiar interpretation of redshifts as velocity shifts leads to strange and dubious conclusions."
If, on the other hand, Hubble had proposed that redshifts were not caused by the galaxies receding from Earth, but by their various but static linear distances from Earth, this would have forced him to conclude that the galaxies did not decrease in their population at large distances from Earth. For this reason, Hubble rejected the linear theory. What interests us most, however, is the motive for Hubble's decision. The motive was to keep the Earth out of the center of the universe. As he puts it in his book on pages 50 and 51,
"Such a condition would imply that we occupy a unique position in the universe, analogous in a sense to the ancient conception of a central Earth. The hypothesis cannot be disproved, but it is unwelcome and would be accepted only as a last resort in order to save the phenomena. Therefore, we disregard this possibility and consider the alternative, namely a distribution which thins out with distance. The unwelcome supposition of a favored location must be avoided at all costs."
but even choosing a universe wherein the galaxies thin out with distance did not solve Hubble's problem. Whether the galaxies thinned out or not, if what surrounded the Earth in all directions were galaxies that all exhibited a redshift, this meant the Earth was in the center of the distribution. Otherwise, we would see as many galaxies blue-shifted as red-shifted. As Stephen Hawking put it in his popular book, A Brief History of Time,
At that time, most people expected the galaxies to be moving around quite randomly, and so expected to find as many blue-shifted spectra as red-shifted ones. It was quite a surprise, therefore, to find that most galaxies appeared red-shifted.
if, as the statistics show, 99.99% of the galaxies are redshifted from our observation point, Earth, it means the universe is geocentric. Ironically, it means that all the efforts of both Einstein and Hubble only confirm the ancient worldview of a central and motionless Earth. So, to keep Earth out of the center, Hubble had to come up with another explanation. The only way to do so, Hubble reasoned, was to eliminate a center altogether and put every galaxy, including the Milky Way in which the Earth resided, on the surface of a balloon-shaped universe that had no center. By analogy, if Hubble could make the universe into a balloon instead of a solid spherical ball, then the universe would have no center, only a surface. This could be accomplished, at least on paper, if they allowed themselves to dispense with Euclidean geometry and, as Hubble says on page 55, quote, adopt Riemannian geometry, which operates in curved space, unquote, and operates in 2 dimensions rather than straight lines and 3 dimensions. In Hubble's new universe, the galaxies would be expanding away from each other as if they were dots on the surface of a balloon that was being inflated. Hubble explains how this universe would work and why he chose it on page 54 of his book. He writes,
All observers, regardless of their location, will see the same general picture of the universe. If we see the nebulae all receding from our position in space, then every other observer, no matter where he may be located, will see the nebulae all receding from his position. However, the assumption is adopted. There must be no favored location in the universe, no center, no boundary. All must see the universe alike. And in order to ensure this situation, the cosmologist postulates spatial isotropy and spatial homogeneity, which is his way of stating that the universe must be pretty much alike everywhere and in all directions.
Today, we often hear cosmologists on popular television shows saying the universe is isotropic and homogeneous. The reason is that it is required of the universe they desire if they want at least some plausible answer for why we see 99.99% of the galaxies with a redshift. An entirely smooth universe would allow no special place, especially a center point that could be occupied by the Earth.
Hubble says much the same on pages 58 and 59 of his book. He writes,
Such a favored position, of course, is intolerable. Moreover, it represents a discrepancy with the theory, because the theory postulates homogeneity. Therefore, in order to restore homogeneity and to escape the horror of a unique position, the departures from uniformity, which are introduced by the recession factors, must be compensated by the second term representing effects of spatial curvature. There seems to be no other escape.
But as Hubble admits that he must postulate recession factors and rely on spatial curvature in order to keep the Earth out of the center, he also admits that these ad hoc additions seem artificial and create serious problems. On page 59, he writes,
To the observer, the procedure seems artificial. Now, in testing the relativistic theory, he introduces a new postulate, namely the recession of the nebulae, and it leads to discrepancies. Therefore, he adds still another postulate, namely spatial curvature, in order to compensate the discrepancies introduced by the first. The accumulation of assumptions is uneconomical.
Hubble was not the only one who understood that the empirical evidence placed the Earth in the center of the universe, and likewise, not the only one who did not like what he saw. 50 years later, the second most famous scientist in the world next to Einstein said much the same regarding Hubble's analysis. In his best-selling book, A Brief History of Time, Stephen Hawking writes,
Now, at first sight, all this evidence that the universe looks the same whichever direction we look might seem to suggest there is something special about our place in the universe. In particular, it might seem that if we observe all other galaxies to be moving away from us, then we must be at the center of the universe.
This is quite an admission from Hawking. Unfortunately, the philosophical biases of the men of Hubble's and Hawking's generation do not allow them to accept a central and motionless Earth as the most obvious answer to this astounding telescopic data. This Copernican bias drove modern cosmology to its presently accepted interpretation of Hubble's data, namely, Instead of galaxies being organized around a common center, as the evidence plainly showed, they insisted, rather, that the universe is merely a balloon-like surface wherein galaxies are said to lie on this curved surface and are spreading out from each other. And most important, Earth is in one of those moving galaxies, not in the center of the universe, for there is no center to a balloon universe. As it was for Einstein in 1905 when he invented special relativity, any ad hoc solution, other than an Earth in the center of the universe, would be acceptable for modern man. The reason was plain. As Hubble put it in his book, quote, "Such a favored position, of course, is intolerable," unquote. Essentially, spatial curvature and homogeneity are modern cosmology's manufactured but necessary ingredients to maintain the Copernican principle, the presuppositional belief that the Earth is not special and inhabits no special place in the universe. Spatial curvature removes the Earth from the center of a three-dimensional universe and puts it on the surface of a two-dimensional hyperspace. As the balloon expands, an expansion that Hubble believed was occurring due to his observation of redshift in all the galaxies, all the objects on the balloon will stay equidistant from one another, and no galaxy could be designated as the center. At the same time, ironically, modern cosmology also claimed that the universe appears flat to us, that is, Euclidean, since we as observers are so small compared to the size of the universe that we wouldn't notice its curvature and therefore it would appear flat to us. As noted in his book, Hubble wanted a homogeneous universe so that it would not be geocentric. This means that as one looks into the universe, everything will appear to be precisely the same, analogous to homogenized milk that has no cream on top and no lumps in the middle. This is otherwise known as the cosmological principle, which then leads to the conclusion that the universe has no distinguished place, and thus no center and no motionless celestial body to occupy a center. It would be the same as if one was in the desert and looked north, east, south, and west, and saw the same sand in each direction with no distinguishing features. After Einstein and Hubble provided the foundation for modern cosmology, all subsequent theories had to be based on a homogeneous and spatially curved universe. Otherwise, it would necessarily be geocentric. As noted earlier, the amount of curvature needed was calculated by Einstein's famous tensor equation, G equals 8 pi tau. The homogeneity that was needed to make Einstein and Hubble's universe feasible was calculated by a Russian physicist named Alexander Friedmann, who adjusted Einstein's equations for this very purpose.
A few decades later, Stephen Hawking admitted the real motivation behind Friedmann's attempt to make the universe homogeneous. As was becoming common in modern cosmology, the motivation was to eliminate a center and Earth's possible occupation of the center. Hawking writes in A Brief History of Time,
There is, however, an alternate explanation. The universe might look the same in every direction as seen from any other galaxy too. This, as we have seen, was Friedmann's second assumption. We have no scientific evidence for or against this assumption. We believe it only on grounds of modesty. It would be most remarkable if the universe looked the same in every direction around us, but not around other points in the universe.
As we see, Hawking quite candidly admits the evidence points to an Earth in the center of the universe, but says he chooses to reject it because it would make mankind too proud. Strange as Hawking's answer may be to a devoted scientist, this was not the first time a philosophical foundation became the basis for how one chooses the universe in which he wishes to live. As we noted earlier, but is worth repeating here, George Ellis, who co-authored a book with Hawking, shows why Hawking must feign modesty to promote an anti-geocentric universe.
People need to be aware that there is a range of models that could explain the observations. For instance, I can construct for you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on observations. You can only exclude it on philosophical grounds. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models. A lot of cosmology tries to hide that.
In the end, we see that the men of Hubble's and Hawking's generation choose their cosmological model based not so much on science, since the science is often ambiguous, but on a commitment to a universe that best fits their philosophy. They are completely devoted to the Copernican principle. All the data they receive in their telescopes or microscopes must be filtered through this foundational belief. One wonders then whether Hawking's claim of modesty in deciding against a central Earth is actually pride in disguise, especially since he has become known for promoting the universe did not need a god to begin it or continue it. According to Hawking, who was an avowed atheist, the universe could start all by itself from nothing. While physicists were tinkering with Einstein's equations to produce the best possible universe to match their philosophical beliefs, a more precise theory of the universe's origin was introduced. It was derogatorily dubbed the Big Bang by cosmologist Fred Hoyle, who saw his steady-state model, which proposed an infinite universe with no beginning and no end, fall to his Big Bang competitors. The Big Bang was the brainchild of the Belgian priest and scientist Father Georges Lemaitre. Perhaps seeking to combine his biblical notions of a Genesis-like beginning with the discoveries concerning the redshift of galaxies, Lemaitre proposed that the universe had a beginning and was not infinite in time or space. But as Lemaitre sought to make the beginning of the universe fit with both Edwin Hubble's expanding universe and Alexander Friedman's homogeneous universe, he faced a glaring problem with the opening words of Genesis, which stipulated that the earth was created first, before the light and the stars and the rest of the universe.
In the beginning, God created the heavens and the earth. The earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God was moving over the face of the waters. And God said, "Let there be light," and there was light. And God made the two great lights, the greater light to rule the day, and the lesser light to rule the night. He made the stars also, and God set them in the firmament of the heavens, to give light upon the earth, to rule over the day and over the night, and to separate the light from the darkness. And God saw that it was good. And there was evening, and there was morning, a fourth day.
Siding with Lemaitre were various Catholic theologians who, by the later 1800s, had already begun to abandon the traditional literal interpretation of Scripture, doing so after the theory of evolution was introduced by Charles Darwin in 1859. Working in the 1930s, Lemaitre likewise decided to abandon the traditional interpretation and limit the divine purpose of Genesis to merely a general statement about the beginning of the universe, but with no concern for details. This same hermeneutic is practiced today in most seminaries and universities, as well as introductory notes in many popular Bibles. Lemaitre thus created a hybrid between Genesis and Einstein. In his view, God began the universe not by creating the earth first, but by creating a cosmic egg. Lemaitre said the egg cooked and exploded, as it were, according to the recipe given in Einstein's general theory of relativity. It would not be until a few decades later, however, that modern cosmology painfully discovered that the Big Bang model had just as many problems as the steady-state model it had replaced, as we will see momentarily. One historical note of importance is that after Lemaitre proposed his Big Bang universe, Einstein determined that he did not need his lambda factor in his field equation G equals 8 pi tau any longer. Since in Lemaitre's new theory, everyone now believed the universe had a definite beginning and was not infinite, Einstein no longer needed to keep the universe either infinite or steady.